sort of one resistivity of resistance without making any difference. So one of the main assumptions of the model is that we connect the local density of vacancies at one of these sites with the local resistivity, and which is, in the case of complex oxides, as I showed, and it was one of our key ingredients, the density of oxygen vacancies. As we increase the density of oxygen vacancies, the local resistivity is increased. So we are going to show how when we apply the electric field, we can move vacancies back and forth from the interface regions to the bulk, or to the bulk to the interface, to both interfaces, and in a way this can be, this gives the change in the local resistivity, and with this we can change the total resistance along the sample. In this case, if we follow along this path, the total resistance is the sum of the total of the local resistivity along all the sides of the sample. I'm going to elaborate on this in the following. So the idea is, as I told you, we have our basic equation in which if we know the local density of vacancies, we can know the local resistivity. So we are going to modify the local density of vacancies as we apply the electric field, and in a way we are going to modify the local resistivity and the total resistance of the sample. As I told you before, we have three different regions. We identified three different regions in our model: the bulk of the sample and the two interfaces. The two interfaces are the high resistive regions of the sample. So in the very basic linear relation that we have established, is the most simple one, it's not the only one, of course. We have these parameters alpha, these parameters A alpha with alpha left, right, or bulk, left interface, right interface, or bulk part of the sample, in which we consider for our, in our model that the values of A at the interfaces are larger than the bulk side of the sample. In a way, we take into account in these A values all the geometric characteristics of the interfaces and the fact that we have high resistive interfaces compared to the bulk interface. So these A values are going to be larger at the interface compared to the bulk. Even though if we want to characterize, for example, two different interfaces, we are going to take two different values from the left and right interface. This is something we can play, and I'm going to show you how, as we change this relation between the A values, we can go through different behavior on the IB characteristics. So the idea of the numerical model that we have established is when we apply a voltage, okay, the voltage B, it's applied between left and right electrodes. So we follow a cycle on a protocol. We will from the voltage from 0 to maximum value, then go to a minimum one, and then to 0. This is a complete cycle. From each time step, the density of vacancies is updated, okay? So when we go from time t to t plus delta t, the density of vacancies is at each side of our conductive path is updated with this transfer rate. This is the probability to transfer vacancies from site A to B, which of course is a sort of rate equation that we solve, in which this probability is going to change with the density of vacancies content at site A, the density of available vacancies that we have at site B, the neighbor site from A, and this sort of Arrhenius activation factor that contain essentially two main terms. One is this constant that characterizes the diffusion, which is the activation energy to move vacancies from site A to B. And this is the main ingredient that comes from the electric field, local electric field that appears, or the local voltage drop at site A. This local voltage drop, it's going to be related with the current and the total voltage applied along the sample and the total resistance of the sample. So the local voltage at site I is the local resistance times the current. The current is known, this is the local voltage, and the local voltage drop is the difference between the voltage at site I+1 minus the voltage at site I. So at each time step we can update the local resistivity of course, the resistance of each of the domains. So the total resistance at each time step can be computed only adding up the resistance along the sample. So the voltage polarity essentially what does is to drive vacancies towards away from the interface region to the bulk side of the sample. Yes? Sorry?
What's the physics of the delta 1 minus delta?
Okay. This is it's a rate equation when you compute the probability from going to site A to B, you need, which is the number of vacancies that you have and the number of available sites or unavailable disposal sites that you have in order to put vacancies. So if you have all your neighboring site full of vacancies, you are going to have zero probability to go from left to right, for example. Okay? This is the usual way in which rate equations are treated. It's transfer of population.
If you have big rains, if the vacancies are small, they are not going to stop each other. I understand exactly what. This is like the Pauli exclusion principle, which I don't see how for
No, it's not Pauli exclusion because it's a classical. It's not Pauli exclusion. You need. If you have all your, you have a finite number of vacancies, okay, and you can put all your vacancies in one site, for example. This could be done. So if this site is full of vacancies, you don't have available room from put another one. This is the very simple explanation as the usual one. When you have to move things from one side to another one, you have to have enough sites. In this case, the local density of vacancies tell you if you can put another vacancy or not. They are not interact. No, it's first nearest neighbor model without any interaction. Of course, you can complicate this as far as you want, but this is the simple one. So one of the interesting things is, as I told you before, is the forming processes. You can start with an eventually uniform distribution of vacancies, but as long as you want that the samples start to switch back and forth, you need to form the sample. In a way, for us to form the sample is to obtain an optimal distribution of vacancies. Look here. This is the left interface. This is the right interface, and this is the bulk side of the sample. As I told you, the interfaces are the highly resistive one in which the high electric fields is going to develop. So we are going to move vacancies towards or in the interface regions, but at the bulk side of the sample, the electric field is much, much lower than the interface. So vacancies tend to accumulate. When you start to form the sample and apply voltages back and forth, vacancies tend to accumulate at the bulk side of the samples close to the interface, okay? And in a way, this is the way in which in our model forming appears. We start from this distribution of vacancies, and after this distribution has been reached, then the samples start to switch, okay? So we need these forming processes, or in a way, this is the optimal distribution of vacancies. From this distribution, vacancies start to move back and forth at this interface or at this interface. That depends on the local electric field and on the symmetry of the sample, as I will show in a few moments. So the idea is we have resistance as a function of the voltage. Instead of characterize the IB curve, we can plot this resistance hysteresis switching loops, which essentially plots the resistance as a function of the voltage. So it's in a way the same information that we obtain from here to from here. But in this way, we can view more clearly how the resistance change as a function of the voltage in one of these loops. This is only the presentation of the way in which we are going to characterize the behavior of the sample. This is a cartoon. I'm going to show you the results. So the first thing that we have analyzed in the case of having a symmetric configuration. As I told you before, we can control the symmetry of our sample with the values of these A coefficients. So if we choose A left and right equal, we are going to talk about a symmetric sample, okay? So these are our model simulation results. We start as a function of different loops or different cycling voltages applied, okay? So we start from 0 voltage and we plot the resistance as a function of the voltage. We perform one loop, second loop, third loop. Well, here is the 5, 6, and 7. Okay? So this is the result. We start from this high resistance, then go to the low resistance, then turn to the high, to the low, and this, with this symmetric configuration, we obtain this hysteresis switching loop that looks exactly the same as this table with left that have introduced some years ago at the Ignatieff group in Texas. So this is the result from the simulations, and these are results taken from Pablo groups with PCMO, in which they obtain exactly, the same kind of resistive hysteresis switching loops. And this is a result from experiments performed by Charlie Acha, here also at Buenos Aires, and Laboratorio de Bajas Temperaturas at the University of Buenos Aires, and from a sample in which, it's based on EPICO. This is rather different from this one. I'm going to explain a little bit later why this behavior can emerge in comparison with this one. But here, one of the first results is that our model simulation can reproduce quite accurately experimental results. So here I'm going to go a little bit deeper in the details, why we obtain these loops and why these loops are correlated with the density of vacancies or with the local resistivity along the sample. For example, if you take, I'm going to show one of these loops and I'm going to follow as a function of the voltage, and from these different points that have been marked here, I'm going to show, which is, I'm showing here also, which is the local density along the sample, the density of vacancies, and the local resistivity. Of course, the local resistivity is proportionally to the local density of vacancies. So, for example, if we concentrate on this left-hand interface, we start at 0 voltage. We have this initial density vacancy profile, which is the black one. As we increase the voltage, we have increased as we increase the voltage, the density of vacancies decrease here, and with the positive voltage, we put vacancies on this bulk side of the interface. So as we increase the voltage, we extract vacancies from this interface and put on the bulk side of the interface. The same happened from this left side interface. So from each of these voltage, we can correlate the high resistance state, okay, with this value, and as we increase the voltage, the transition from the low resistance state is correlated with this decrease in the oxygen vacancies content on this interface and this interface. So when we observe the resistivity along the sample in the low resistance state, we see that the resistivity, the local resistivity diminishes at both interface, and as we add up all the resistance, we have the two-terminal resistance that give rise to the low resistance state. And in the same way, we can follow and characterize the different profiles of vacancies with the profile of resistivities along the sample as we increase the voltage. Of course, when we change the polarity, we can also, repeat the same arguments, but of course injecting vacancies instead of taking vacancies away from the interface. So when we inject vacancies, we also, again, increase vacancies, increase resistance, okay, at both interfaces, and the total resistance increase. So we can go from symmetric to asymmetric devices also, okay? We can change the values of the A coefficients. So for example, in this, here we show if we take both interfaces with equal value, we have the symmetric profile. When we go from this very asymmetric profile, we have different ratios. For example, here is 40, the ratio between left and right interfaces, and this is correlated with experiment performed on symmetric or asymmetric devices with different contact electrodes. So also, we can think instead, up to now I talk about two-terminal measurements or two-terminal configurations. Another thing that can be done, and had been done here also in Pablo Levy's group, they also concentrate in the change of the resistance at the interface. Instead of doing a two-terminal measurement, you do a 3 or 4-terminal device, you can apply pulses of current or voltages between A and D electrode, and you can concentrate on the local resistance at this, the voltage drop between A and B or C and D. In a way, you can measure the left interface resistance or the right interface resistance. So these are plots from the AB, the left interface, and the right interface. And the main message of these results is the sort of complementarity effect that happens. When one interface is in the high resistance state from the same voltage, the other interface is in the low resistance state. So in a way, the complementarity between contacts is another ingredient that takes into account the fact that the interfaces are the one which are the active one for switching, and in a way the resistance of both interfaces tend to switch in opposite directions. How much time I have in order to? 5 minutes only. Oh my God. Okay. So we can concentrate on some of two interface contributions. So we can construct all the resistance, the two-terminal resistance, for example, here in the table with lefts, as a sum of the right resistance and the left resistance, and in a way we see that these two resistance add up in series in order to have the total resistance of the sample. In a way, at the interface is the one that switch, and the bulk side of the sample, nothing happens. That's the message. Well, I'm going to skip. Well, we have performed here in Buenos Aires many experiments. One of these one is, for example, if we, instead of construct one hysteresis switching loop, you can fix one value of the voltage and goes through different paths in a way that you can control the on-off ratio if you start from different initial voltages. And with our simulation, we have also obtained this, what we call mini loops. And with this, each one of these mini loops, you can have a definite and very controlled profile of vacancies and of electric fields along your sample. So in a way, you can tailor or design different on-off ratio starting from different original voltages, and you can go through different paths. The other problem that we can try to tackle also is the problem of endurance of degradation. What is the origin of degradation of these samples? Well, there are many explanations, and most of you have talked about that. But in our model, it's very simple and obvious what is the origin of degradation. And in fact, it's the way that as the electric fields and the bulk side of the sample are lower than the interface region, when you put vacancies on the bulk side of the sample, you don't have on this side the same kind of electric field to put vacancies now again inside the interface. So at each cycle you are going to create a sort of reservoir of vacancies on the bulk side of the sample. So when you apply, for example, here I show you, in this interface, titanium LPCMO, we start with this initial resistance, low resistance state, okay? this is the, for example, the red value of the total resistance. You apply a voltage that drives vacancy inside your interface. You enlarge the local resistivity. You enlarge, this is the density of vacancies, the local density of vacancies, so your resistance of the interface is going to be increased. I'm now focusing on one interface. Suppose that they are performing these 3 terminal measurements and only measurement all the contact resistance of one of the interface. So what happens when you apply a pulse of the other polarity? Okay, the problem is that now you push vacancies away from the interface, but in a way you don't have exactly the same profile of electric field. So again, when you go to the low, to the high, and then try to go back to the same value, you don't reach the same value because you don't have enough electric field to drive all the vacancies inside again. So this is the origin, in a way, from the gradation. So once we understood that this could be, the main origins, we tried to perform some strategies to overcome the gradations. And well, experimentally here they can perform a symmetric pulsing protocol in which we have established, different reset and set currents, optimal values from set and reset current that establish an optimal value from the high and low current value. So in a way, you have to apply an asymmetric pulsings in order to try to introduce your vacancies again at the interface. So one solution is this asymmetric pulsing. So I'm going to skip, well, this is the optimal value from the set reset. As you change this value to another one, your on-off ratio decrease and the endurance of the sample time. So, well, we implement another protocol, but I'm not going to talk about this. I'm going to spend 3 minutes, may I? And told you some new results that we have on binary oxides. As I told you, up to now, I am talking about our model, which was motivated on complex oxides, inhomogeneities, oxygen vacancies, and this interface type of switching. Here, Nestor Gensi is going to give a talk on this titanium dioxide sample that he had here growth at Buenos Aires, and he's going also. He have a poster, so details are going to be in his talk and in his poster, but I show you some measurements of him in which on these samples, aluminium, titanium dioxide, gold. So these samples need a sort of negative forming, okay? And while the forming is performed, then the sample, okay, we have these IB characteristics, but in terms of the resistive loops, we have the low resistance. This is current as a function of voltage. So this is the low resistance and this is the high resistance. The first thing that we can extract from the experiments, and this kind of resistive hysteresis switching loops is a one interface type of resistor. If you remember the resistive hysteresis switching loop that I showed you before from left or right interface, this is the way one of these loops look. So, and in fact, that's the way we believe things happen, because the active interface for switching is the golden dioxide titanium interface. This interface is mostly ohmic, because when the forming, we need a negative forming, okay? So negative forming is to move but this is the oxygen vacancies filament, okay? And here some oxygens remains. Remember that different from complex oxides, in binary oxides, oxygen vacancies act as carrier dopants, okay? So as we increase the contact of oxygen vacancies, we create a sort of metallic filament in our sample. So this is the main difference. So we have this ohmic-like interface that doesn't switch, and this is the active interface for switching. And this corresponds exactly with this kind of behavior that Nestor obtained in his experiments. And well, the idea is we have updated the model. Okay, we have many of the ingredients to proceed with the model, but the main difference is now we have to change the relationship between density of vacancies and resistivity. Now in the binary oxides, as I told you, as we increase the density of the oxygen vacancies, we increase conductivity. So the main difference in our model is a simple one. The conductivity increase with the density of oxygen vacancies, okay? So from conductivity we can extract resistivity. And this is the initial profile of oxygen vacancy that we have along our sample. I am concentrated in this region. This is the right part when I flip this filament to the horizontal position. This is the gold interface, titanium dioxide gold interface. This is titanium dioxide, and this is aluminum, which is essentially ohmic. So we have the filament, okay, the conductive filament with a high content of oxygen vacancies, and our regions in which the content of oxygen vacancies is lower because we have more oxygens there. So exactly we perform the simulations, but with this update profile that relates resistivity decrease with the content of oxygen vacancies. And well, these are our first results on the model, but in a way we reproduce qualitatively the hysteresis switching loop. Here, I again emphasize, is current. This is the low, this is the high resistance state, and also here we plot resistance as a function of the voltage, and we obtain essentially the qualitative loop that had been obtained experimentally. And with this, as I mentioned before, we can correlate each of these, for example, region of the RB curve with the density vacancy profile, and if we concentrate here on the right part in which resistive switching takes place, as we see, as we increase the content of oxygen vacancies, for example, this is the blue one, okay? We are here, okay, sorry, we have in the low resistance state for the green and in the high resistance state for the blue, which we have lower density of vacancies at the interface. So with this I finish, sorry for the delay, but I essentially want to spend 1 minute instead of the conclusions to of course show my collaborators, because of course, Marcelo, we have been working on the theoretical model since many years ago. And here also Pablo, and Nestor, I put his name in blue because he performed many of the experiments that I have been showing in the last part of the talk, and he also is going to give a talk on this. And also of all the team, the students and the collaborators, Pablo, Ruben, who is not here, he collaborated with us in the theoretical model. And of course, Isao, that he's not here, but he was our inspirator because he was the first that suggested us the idea of working on this field. So, okay, and Charlie, who is sitting here, and he's going to give a talk also on resistive switching. So thank you for your attention, and sorry for the delay.
You, Maria Jose, thank you very much. Question?
Yeah, so apparently Stan Williams out of HP had devices for which are very similar to this. And what Georgi explained to me is that they try to fit, when the resistance starts to drop. It goes rather abruptly. It's not really a kink, but it is very sharp, and they try to fit it with a weird double exponential function, which they try to justify partially by saying that the resistance of this Schottky barrier or something has a tunneling. None of this is in this model, but it seems very similar. So do we actually have an understanding what is the functional form of the resistance versus voltage when it starts to drop?
Essentially the functional form, no, we don't understand.
Well, but what's your feeling?
You have, of course, you're talking about a complex, because the behavior is rather different.
Titanium oxide.
And titanium dioxide, okay. So the idea is that you have your filament and you have a narrow region on your interface in which you can move vacancies back and forth in this narrow region. So essentially what you put are vacancies, more vacancies or lower amount of vacancy depending on the strength of your electric field, okay? But in a way, something that I don't talk about, but which is extremely important in all the experiment is the compliance current, because if you, when they perform the experiment, I don't want to talk on experiment because I didn't perform that, but which is important is, as you might know, if I don't control the compliance current, I can form a complete filament in a way that the sample doesn't switch on the bipolar way. If I have a complete filament, the sample at least will switch on the unipolar or the no polar way, and I have to have some Joule heating mechanism effect to destroy it and reconstruct the filament. But in a way, to answer your question, I don't have exactly.
My question was simpler. That in their interpretation, the reason why you have a rather sharp IV characteristic was because of quantum tunneling.
But it's not necessary quantum
yes,
tunneling because the
question.
activation. I mean, all thermal activated processes. You don't need to have a tunnel barrier. You need a sort of Arrhenius factor, an exponential. So it could be thermal, it could be quantum tunneling. But
yes,
all those mechanisms are going to give some nonlinear
I agree.
IV behavior.
Okay.
Other comments, questions?
Can you show, did you investigate, for example, time dependence, like a retention? I mean, how stable is one vacancy configuration, for example?
I don't remember. I think that we have some experiments of time retention, but I mean, in our model, we don't have any processes. Well, you froze the configuration because you apply the voltage and you don't have any relaxation mechanism that, of course, happens in reality. So for each voltage profile, we have a fixed configuration. In one time step, we move vacancies and vacancies stay there. So in a way, this is a weakness of the model, if you want. We don't have any time-dependent mechanism in going to disturb the profile of vacancy that we established at time.
But the model basically says it's a steady state solution.
Yeah.
Maria, it's just an open-ended question from me. You guys had the original model where the resistivity was proportional to the vacancy density, and you showed this nice hysteretic resistive behavior. Then in this new model which you reported, you really reverse that, and now you, in the new model, the resistivity is inversely proportional to the vacancy density, and once again you are finding hysteretic resistive loops. The details are different.
The details are different.
So I'm just inviting you to speculate that if you are changing something so dramatically in the model and the key features remain, is there a message to some more general picture, or what's the real driving force if you change that piece and you still get the same hysteretic behavior?
No, because I mean we have changed in a way. We have one thing that is important is to realize that now we have a sort of a filament in what most of the filament is a sort of ohmic one. So you don't have a strong electric field. The activation, this is parameter B naught that I have put a number of activation energy from moving vacancies. This is something that's going to be different, quite and very different from the side of the sample in which we have the conductive filament and the side of the sample in which we have the resistive switching taking place. This is one of the change, and the other change is the relationship of the ratio between the different A's, because if you look in detail here, I didn't have time, but these B in a way are not play different roles than the A, because here what we are saying, as we increase the number of vacancies, we increase conductivity. So the region of the sample that has more density of vacancies is the in a way, is the ohmic region of the sample. So these B are lower in the ohmic region of the are higher in the ohmic region of the sample compared to the region of the sample in which resistive switching takes place. So in a way, the role of the A's are also interchanged. So in a way, the model is very phenomenological, and it can be understood that if you can drift vacancies back and forth with different voltage energy profiles, but we don't think that we have changed nothing drastically in the model. There's nothing drastically changed, but if you can increase the oxygen vacancy content and we can increase the conductivity, okay, this is the outcome of the model. This is perfect. This is nothing which is essentially changed in the model.
So I guess we are ready for the coffee break.